Hello students, and welcome to section 7-3, multiplying special cases. Today we're going to be taking a look at a variety of special cases. To start with, in example 1, we're going to determine the square of a binomial. So for part A, why is a plus b quantity squared considered a special case when multiplying polynomials? First, we're going to go ahead and assess using the distributive property, and we're also going to use a visual model to pair with this. So if we were to take a plus b quantity squared, we were technically supposed to rewrite it with two different binomials side by side of which are the same. The reason, anytime you square something that has more than one term, you must write it twice. The side-by-side model, as you can see, it also includes distribution, which I'll explain using the model, but in the sense of distribution and the model kind of together, we'll use, in a sense, like the FOIL approach we learned, but in technical terms, they just distribute a times a plus b, there it is, or show it as what you will do in the next step, setting up for distribution. And then similarly, you'll take b times the quantity, again, a plus b. Turns out with our visual off to the right, we do have some pretty nice things to tie to. But let's go ahead and finish here with the algebra before we make that connection. Distributing the a and distributing the b lends itself nicely to a squared plus ab plus ba plus b squared. We have like terms in the middle, ab and ab or ba. We can flip those and technically it's the same as that. So those two like terms add to 2ab. So the algebra speaks to a squared plus 2ab. Okay, I'll scroll down actually here. A squared plus 2ab plus b squared. The first term squared, a squared, twice the product of the first and last terms, so 2 times those two terms, outside and inside, in the FOIL context, if you think about it that way. And as they describe it, the first and last terms, which is also an acceptable way to look at it, as we remember from foiling and also distributing. And then the last term squared. The last term squared simply is just b squared. In terms of the depiction off to the right, this visual model, in a sense like we've seen with algebra tiles in the past, we have a by a. We have a by b. The blue tile is a square a by a. The green tile is a rectangle a by b. And then the smaller yellow square, not rectangle, these are rectangles, and these are squares, of course. This yellow square is b by b, so b squared. So the way we've kind of observed in the past, or in some cases, of course, adding our tiles together, we're, in a sense, adding the edges of the dimensions here of the square and the green rectangle, the blue square and the green rectangle. So these edges add up to a plus b. Well, these edges also add up to a plus b. This little yellow square in the corner is finishing the complete square here, in a sense where, look, a plus b by a plus b. The green rectangles, again, are a by b units, so their areas respectively are a times b, and we have two of those, so ab times 2. I've already denoted a times a, or at least you can see here that it's a squared. We've denoted it in the past, but there you have it. And then last but not least, we have one yellow square, which is b by b, so b squared. So it's kind of nice how we can take this quantity, a plus b quantity squared, so a plus b times a plus b, right? Just like you see here in a different sense. So you are squaring, quite literally, you're squaring a binomial, and you're looking at it as a full square, a completed square, which is kind of neat if you think about visually how that ties together. Again, if you add your terms, you end up with this polynomial. Turns out that this is the result every time that you square a binomial. There's a pattern. The pattern always fits the following kind of model. A plus b quantity squared is always equal to a squared plus 2ab plus b squared. So for part B, what is the product of 5x minus 3 quantity squared? Well, we see here it's a binomial squared. So use the pattern we found in part A to find the square of a difference. So we're going to go ahead and take 5x minus 3 squared, rewrite it as 5x plus a negative 3 squared, rewrite the difference as a sum. And then we're going to continue by really rewriting things in a way, again, where you have the first term squared. These two terms will be multiplied, right? Whether you expand it out or not using FOIL, they're showing the pattern application. So it will end up where you have 2 of these terms multiplied. So 2 of 5x times negative 3, and then lastly, negative 3 quantity squared. That is a direct application of the pattern. Now, albeit the sign is not going to be positive in the end because this negative will turn it negative, but the idea is very much the same. And there you have it. There's the pattern as I described, a squared plus 2ab plus b squared. Finish it up. You do have some terms to follow up with regards to multiplication. All right, this ends up being negative 15x times 2, so negative 30x. This, of course, ends up being 9, so your final answer, the product of 5x minus 3 quantity squared, or 5x minus 3 times 5x minus 3, which would be a better way to kind of assess that, ends up being 25x squared minus 30x plus 9. When I say make the assessment in correlation to part A, all right, rewriting the original problem as 5x minus 3 times 5x minus 3 will work just as well in most cases as what we just did with the pattern. The pattern works phenomenally well on most questions, but so does foiling. Okay, it might take you a little bit longer in some of those situations, but you end up with the same exact answer if you were to foil it. Example 1c. How can you use the square of a binomial to find the product of 29 squared? So we're going to take a look. This is a kind of a non-algebraic approach, but it does help with what we've done already to kind of model it. So rewrite the product as a difference of two values whose squares you know, such as 30 minus 1 quantity squared. Then use the pattern for the square of a binomial to find its square. Now, frankly, we could type in 29 squared on our calculator and get our answer. However, I think the goal here should be to try to see if you could do it without a calculator, or at the very least, see if you could tie it to the pattern we just learned. So 30 minus 1, we know that's 29. And we're going to write it either as 30 minus 1 times 30 minus 1 in another set of parentheses, or as they describe the pattern. I do believe the pattern or foiling should work just as well. Here's the pattern. So you can see they took 30 minus 1 quantity squared. The pattern speaks to a squared plus 2ab plus b squared. This is, of course, 900. You could test this if you'd like on your own. If you're having difficulty doing this without a calculator, let's say. These multiply out to negative 60. And then this ends up just being 1. So then from there you have 900 minus 60 plus 1, which ends up being 841. And yes, if you double check on your calculator, 29 squared is in fact 841. So in general, you can use the square of a binomial to find the square of a large number by rewriting the number as the sum or difference of two numbers with known squares. Again, 30 squared being something pretty straightforward, I would argue, without a calculator. Similarly, negative 1 squared. Example 2. Find the product of a sum and a difference. What is the product of a plus b and a minus b? Okay, we're going to dig into this in a very similar manner, but we are going to end up with a pattern-based approach that is even, I think, more simplified than the last pattern. Use the distributive property to find the product. So here we go. If we distribute a plus b times a minus b, or FOIL, again, that's the other approach to consider, you'll end up with the following. I'll scroll down a little bit here. A times the quantity a minus b, or a squared minus ab in the next step. B times the quantity b, a minus b, or ba minus b squared in the next step. The middle terms are going to drop out because they are opposites of each other. So these terms, because they are literally opposites, they cancel or drop out. Or if you think of it just adding to 0, right? Those add, because they're like terms, to 0. So your pattern, look at this, yields a squared minus b squared. Probably one of the neatest patterns we're going to look at today, where the first term is squared and the last term is squared. So in the event that you take a plus b times a minus b, you'll always get a squared minus b squared. The name of this pattern is called the difference of two squares, or the difference of squares. Same thing. The product of the sum and difference of the same two values results in this idea, this difference of two squares. What is the product of 5x plus 7 and 5x minus 7? You can FOIL or distribute, same thing. FOIL is just a different kind of set of steps with with distribution still being done. Use the pattern you found in Part A. We'll do it more quickly, of course, with the pattern in mind, and here we go. When you see this particular nuance where the signs are opposites, one is 5x plus 7 and the other is 5x minus 7. This term is your a, so a squared. This term is your b, so b squared. Notice the sign is always minus because it's the difference of two squares. That's always the case. If you FOIL it, you'll find that 7 times negative 7 obviously becomes negative 49, or negative 7 quantity squared, which is what we're about to finish with. So there you have it, 25x squared minus 49. The product of these two binomials ends up being 25x squared minus 49. It's the difference of two squares, as we see. Okay. I do recommend that you maybe check your answer in a sense by FOILing to kind of prove out that the pattern works in this particular case. Once you get the hang of this, you won't need to do FOIL necessarily on these special pattern applications. Part C, how can you use the difference of two squares to find the product of 43 and 37? Okay, similar to a problem we have already seen where we want to rewrite these numbers maybe, not necessarily using variables in your final answer, but characterizing it like a pattern basically. Speaking of which, rewrite the product as the sum and difference of the same two numbers a and b. 43 and 37 are each 3 units from 40. So we can write 40 plus 3 as 43, and we can write 40 minus 3 as 37. So in a sense, because again we know by FOILing these, your middle two terms are going to cancel every single time. We don't even need to write them. All right, so in a sense, we can skip that step if you were to FOIL, or of course, if you're using the pattern, simply take a squared, 40 squared, minus b squared, so 3 squared. Quite nice. So 1600 minus 9. Off to the right, they kind of describe how that could be modeled in conjunction with, or how it is modeled in conjunction with the pattern we discussed. This subtracts to be 1591. You can use the difference of two squares to mentally find the product of large numbers when the numbers are the same distance from a known square. That is a key part to the question. They have to be the same distance from a known square in order for this to work. But it does work out quite nicely. Technically, using a calculator on this may not be necessary. Don't feel like you have to do it without a calculator, though. It's just something to kind of nicely see be modeled after the patterns. All right, example 3. So we're going to go ahead and take a look at applying the square of a binomial. A graphic designer is developing images for icons. The square pixelated image is placed inside a border that is 2 pixels wide on all sides. If the area of the border of the image is 176 square pixels, what is the area of the image? Now I'm not going to finish this question, but I do want you to take a look at the picture. Notice x plus 4 by x are the dimensions. Let x represent the length and width of the image. So in this depiction, we're going to go ahead and formulate, compute, and then of course interpret our steps. The final answer, I'm going to allow you to take a look at that on our secondary page so you can see the completed notes on your own, but take a look. You will be modeling this after a square of a binomial.